about to relate the greatest story ever told. The story of the origin of you and me, everyone you know, and indeed the whole universe. The story begins on planet Earth in an ordinary town in Britain, perhaps similar to your own hometown. Looked at from a satellite circling high above the atmosphere, this town might look something like this. You can even see the river running through. On a fine day, the satellite can see the entire British Isles. And from a wider perspective, the British Isles can be seen to lie off the coast of continental Europe. Looked at from further out in space, the Earth is spectacularly beautiful. A sphere, nearly 13,000 kilometres in diameter, weighing 6 trillion kilograms, with the blue oceans painted over by white clouds. The brown landmass of Africa can clearly be seen. Zooming out further into space, the Earth is seen to be a blue, white and brown planet. Our nearest planetary neighbours are Venus and Mars, which together with the Earth make up a system of 9 planets which orbit the Sun. Notice how the closer planets are orbiting faster than the more distant ones. Everyone knows that the Earth orbits the Sun in a year. Mercury is the planet that's closest to the Sun and only takes 3 months to complete its circuit, while the most distant planet, Pluto, takes a leisurely 248 years to go round the Sun. Moving away from the Sun, it appears to be just another star in a huge swarm of stars which make up our own Milky Way galaxy. The radius of the Milky Way's disk is about 80,000 light years, and it contains about 300 billion stars, of which our Sun is just one. The Milky Way is a spiral galaxy, but there are other kinds of galaxies too, such as the ones shown here. The universe is made of clusters and superclusters of galaxies, such as the ones photographed by the Hubble Space Telescope and shown here. It's natural to ask the question, where did all this come from? It's quite surprising to realise that over the past 50 years, during the lifetime of your grandparents perhaps, the question has finally been answered, and the answer is mind-boggling. Yet there's sufficient evidence now to accept it as scientific fact. The answer is that about 13 to 14 billion years ago, the universe was created at a single point in a cataclysmic event that we call the Big Bang. When we say that the universe was created, we mean not only the matter in the universe, but also space and time themselves. The universe wasn't born fully formed, but like ourselves, has grown and evolved in time. The early universe was about as different from the present one as it's possible to imagine. Whereas today the universe is cold, the temperature in deep space is about minus 270 degrees centigrade, or 3 degrees above absolute zero, the early universe was billions of degrees. And whereas the present universe is large, being at least 10 billion light years across, the early universe was very small, much smaller even than the size of a single atom. The primordial fireball was so hot that the atoms which make up all the familiar matter in the present-day universe would have been ripped apart into their constituent basic particles, which are much smaller than the atoms themselves. The early universe consisted of a dense soup of particles at very high temperature and pressure. These particles are moving very fast and collide with one another. If we slow down the movie, we can see that there are several different types of particles which make up the soup. The first types of particles are called quarks. The lightest quark is called the up quark, which has an electric charge of positive 2/3 as compared to an electron which has a charge of negative 1. The next heaviest quark is called the down quark. The down quark has got an electric charge of negative 1/3. The up and the down quarks are all that are required to make protons and neutrons, which together with electrons make up all the known atoms in the present-day universe. However, there are more exotic types of quarks which are heavier, such as the strange quark, discovered in 1947, which has got the same electric charge as the down quark, but is about 10 times heavier. Then there's the charmed quark, discovered in 1974, which has the same charge as an up quark. The charmed quark is quite heavy, in fact, about 1.5 times heavier than a proton. Heavier still is the bottom quark. The bottom quark has the same electric charge as a down or a strange quark, but weighs in 5 times heavier than a proton. Finally, the real heavyweight champion of the quarks is the top quark. The top quark has the same electric charge as an up or a charmed quark, but a mass about 180 times that of a proton. For every particle, there's an antimatter particle, which has the very same mass but the opposite electric charge. To mark the difference, we show them with a line over their symbols. Apart from electric charge, the quarks and the antiquarks also carry a new kind of charge called colour charge, or colour for short. Now don't think of this as real colour, it's just a name. Colour is what makes the quarks stick together in groups of 3 and in a proton or a neutron. The second type of fundamental particles are known as leptons, the most familiar example being the common or garden electron. Just as there are heavier copies of quarks, so there's a heavier version of the electron. It's called the muon. It's about 200 times heavier, but carries the same electric charge of -1. There's also an even heavier version of the electron called the tau lepton, which is nearly 4,000 times heavier than the electron is. Each of them have the same electric charge of -1, like the electron. Leptons also come in electrically neutral forms called neutrinos, which interact so weakly and have such very tiny masses that they were called ghost particles by the scientists who first studied them. It turns out that there is a separate type of neutrino associated with each charged lepton. Associated with the electron, there's the electron neutrino. Associated with the muon is the muon neutrino. And associated with the tau is the tau neutrino. The leptons comprise all the charged leptons and all the neutrinos together with their antiparticles. None of the leptons have colour charge. A completely different group of particles are the ones that carry the forces. They're called gauge bosons, or bosons for short. The most familiar is the photon. A photon has no mass, no electric charge, but couples to all fundamental particles that do carry electric charge, including the quarks and the charged leptons. The Z boson is like a massive photon, being electrically neutral, but with a mass that's over 90 times that of a proton. As well as coupling to charged particles, the Z boson also couples to neutrinos. Then there's the W boson, which has an electric charge of +1 or -1, but is otherwise quite similar to the Z boson. The W boson has a mass that's 80 times that of a proton, and it too couples both to charged particles and to neutrinos. Heavier quarks and leptons can decay into lighter ones by a type of radioactivity known as beta decay, in which the W boson is involved. The last type of these bosons is called the gluon. A gluon is massless and electrically neutral, just like the photon. It's when the gluons flit from one quark to another the quarks stick together to make protons and neutrons. Gluons themselves carry colour charge and so can stick to one another. Photons, however, can't do that trick. We've already said that the cosmic soup was dense and very hot at very early times. Let's now be a bit more quantitative about this. We'll go back to a time that's a millionth of a second after the Big Bang. That's 10 to the minus 12 seconds. And then the temperature of the soup was 10 to the 16 degrees centigrade. It's an amazing fact that all the fundamental particles in the cosmic soup initially had zero mass. They only gained their masses about 10 to the minus 10 seconds after the Big Bang, when the temperature had cooled to 10 to the 15 degrees and the average energy of a fundamental particle was about 100 GeV. At this stage, a mysterious field called the Higgs field, which fills all of space just like water fills a swimming pool, underwent a phase transition, which is rather like water freezing. And when it did, the fundamental particles then gained their masses. Let's take, for example, the case of the Z boson and the top quark. Initially, they were massless, but when the Higgs field froze, they received large masses and then began to decay. When the average particle energy falls below that equivalent to the mass of a top quark, then the particle decays into a W boson and a bottom quark. When the average energy falls below the Z boson mass, this too decays, for example, into an electron and a positron. Similarly, the W boson can decay into an electron and an antineutrino. At higher energies, the particles can be recreated by the process in reverse, but at lower energies, there's insufficient energy to recreate the heavy particles, and so the numbers in the cooling cosmic soup begin to dwindle. A microsecond after the Big Bang, the energy's now fallen to 1 billion electron volts, 1 GeV. At this energy, the up and down quarks have become too sluggish to escape the attractive forces caused by the gluons. They become bound together into protons and neutrons. Similarly, the antiquarks become bound into antiprotons and antineutrons. Quark and an antiquark can form a meson, in this case a pi meson or pion. However, soon after their formation, most of the antiprotons and antineutrons annihilate with protons and neutrons, leaving only a very tiny excess, about 1 proton or neutron for every billion that had been produced originally. Why such a tiny excess remains is a complete mystery. The soup at this stage consists simply of electrons, positrons, neutrinos, antineutrinos and photons, plus the odd proton or neutron which survived annihilation. It's now time for the electrons and positrons to annihilate into photons. Just as with the protons and neutrons earlier, in this case, only 1 electron is left for every billion that was there originally. In just 3 minutes, the universe has cooled sufficiently that the small excess of protons and neutrons join together to make the simplest nuclei, such as the helium nucleus, consisting of 2 protons and 2 neutrons. So in the time that it would take to boil an egg, the basic building blocks that will eventually form atoms are in place. However, it will take another 380,000 years before the universe is cooled enough that atoms themselves can be made. At this point, the electrons bind with the protons and the nuclei of helium to form atoms. Once all the electrons are bound into neutral atoms, the universe just consists of electrically neutral matter. Since photons couple to charged particles, they no longer scatter incessantly, and the universe becomes optically transparent, rather like a fog clearing. In fact, the cosmic microwave background radiation has travelled unhindered from that long-ago time of last scattering, 380,000 years after the Big Bang. Some 13 billion years later, we can detect it with satellites, telescopes, or even your own television set. Earlier on, we mentioned the Higgs field, which fills all of space rather like water fills a swimming pool. Associated with the Higgs field is a Higgs particle, just as the photon is associated with the electromagnetic field. To date, the Higgs particle has not been discovered and is the missing piece in the Standard Model jigsaw. There must also be other particles which are responsible for the dark matter in the universe. These are yet to be discovered. We don't know for sure who they are, and we denote them with question marks. So we know a lot about how the universe began and what it's made of. However, many questions remain to be answered, and here are just a few. Why was there a tiny excess of matter over antimatter? Just 1 in a billion, without which we wouldn't be here. What's the nature of the dark matter particle, represented earlier by a question mark? And why is the universe so large? And why is the microwave background radiation so uniform? These are cosmological questions, but they may find their answers within the realms of particle physics. For example, the recent discovery that neutrinos have mass has led to theories in which neutrinos and antineutrinos are the same. What's more, these theories predict that there are very heavy neutrinos which could even be responsible for generating the tiny excess of matter over antimatter when they decayed in the early universe. Further theories called supersymmetry predict that every known fundamental particle has a heavier superpartner. Although the heavier ones are unstable and decay, the lightest one is predicted to be completely stable and could be the dark matter particle. For example, this might be the superpartner to the photon, called the photino. Presently, at the CERN laboratory in Switzerland, there's an experiment underway called the Large Hadron Collider, which could discover the superpartners to the known fundamental particles and prove the supersymmetry idea to be correct. Such a discovery would pave the way towards understanding some of the deepest questions in the universe. Finding the answers is an exciting adventure. Might you be part of it?